Hello friends, welcome back to the tetrahedron chemistry classes. So in today's class I am going to discuss a very important topic from the thermodynamics, and as well as this topic is very much related to the metallurgic operations also. Okay, and the name of the topic is the Ellingham diagram. So today I am going to discuss the Ellingham diagram. So what you can do, you can focus on this particular lecture and simultaneously you can make your notes also, because this topic is very important for the examination point of view, especially if you are in BTECH first year. Then this topic is of particular importance, right? And along with this BTECH first year curriculum, this topic is very important for NEET and JEE examinations also. Even it is very important for the BITSAT also, right? So as you can see, you can follow my cursor and I'll use my pen as and when required. Okay. So this you see Ellingham diagram. So what is the use of the Ellingham diagram? You can see this point number 1, right? You can see here this point number 1, which is saying that thermodynamic feasibility of the pyrometallurgy. That means if you are doing the metallurgy, I hope you know what is the metallurgy. Metallurgy is the extraction of the pure metal from its ore, right? And when you do the pyrometallurgy, right, pyrometallurgy means you see high temperature metallurgy or the extraction of the metals from the ores at very high temperature. So when you are doing this pyrometallurgy, then what is the thermodynamic feasibility and what are the thermodynamic parameters which makes the reaction spontaneous and you will get your metal easily from the ore, right? So here what I have written again, pyrometallurgy usually applicable to get the metals from their oxides, right? So whenever you have the metal oxides like say MO type of metal oxides or M2O type of or M2O3 type of the metal oxides, right? Then you can reduce then metal oxides to get your metal, right? But sometimes you see the metal sulfides and metal chlorides may also be used to get the metals, right? So this is the third point, and you see second point I have covered, third point I have covered. Now this is your fourth point. Ellingham diagram is a graph plotted between the standard delta G of formation versus temperature. That means this standard gives energy formation of your metal oxide, right? So delta G, this is this zero which I have put it as superscript in on this delta G. It shows the standard nature, right? And F stands for the formation. So delta G, standard delta G formation of the metal oxide, right? This would be plotted versus temperature, and of course your temperature would be in degree centigrade. Sometimes you may also take in the Kelvin also, right? And then the last point, your what is the unit of your Gibbs free energy or your standard Gibbs free energy? It is either you can take in the kilojoule per mole or you can also take it as in the kilocalorie per mole, right, of oxygen. Please remember, this is the unit for delta G standard of formation in kilojoule per mole or kilocalorie per mole of oxygen in the Ellingham diagram. Please remember, this is very important. Now see, you can see here, next is what? ED. ED actually I am taking the abbreviation of the Ellingham diagram, which is ED. ED is used to predict the feasibility of the smelting, right? So if you know what is the smelting, then it is quite good, and if you don't know what is smelting, let us take around let us take some point which are basics of your metallurgic operations. First of all, you see what is smelting. Smelting is nothing to get the metal from their corresponding oxides. So if you have the metal oxides and you are reducing those metal oxide to get the metal, then it is smelting. But sometimes you can see you also use the process of the calcination to get the metal from the ore. Why? See, sometimes you are not having your oxides, but you are having the carbonate. So whenever you are getting the metal from the carbonate, as you can see I have written here, right, this process is known as the calcination. To get the metal from their corresponding carbonates is the calcination. And last is the roasting. What we do in the roasting, we generally get the metal from their corresponding sulfide. So sulfide, when reduced back to the metal, right? Then it is roasting. Carbonates, when they are reduced back to the metal, then it is your calcination. And oxides, when they are reduced back to the metal, then it is smelting. So basically, in case of the Ellingham diagram, we are always interested in the smelting. That means we are always interested in the decomposition of the metal oxide to get the metal. This is something very, very important. So these are the point I have covered, the point number 1, 2, 3, 4, and your next point, right? The another very important aspect, right? Because we are discussing the thermodynamic principle of Ellingham diagram. That means we need to use some thermodynamic expression, and this thermodynamic expression is nothing but it is Gibbs-Helmholtz equation, right? So you can do pronunciation according to you, but I say this equation as the Gibbs-Helmholtz equation, which is nothing but delta G equals to delta H minus T delta S, which I have written here. Delta G is the change in the free energy, delta H is the change in the enthalpy, T is the temperature which you can vary, right? And delta S is the change in the entropy. These three parameters are very, very important. If you know the basics of the thermodynamics, then you are much aware about these three parameters and what is the significance of the sign as well as the magnitude of these parameters in order to get the spontaneous reaction. Say for example, if you want to do the spontaneous reaction, I have written here for spontaneous reactions, delta G should be negative, not should be, it must be negative, right? Delta G must be negative if you want your reaction to proceed spontaneously, right? And more the negative value, more is the spontaneous nature of the reaction. That means you have been, say for example, if you have been given two different reactions and you have been given the data for the delta G for these two reactions, and the questions you have been asked like that, which one is more spontaneous? So higher the negative value, say one is having the negative 500 and another one is having the negative 800. So negative 800 kilojoule per mole or kilocalorie per mole value would be more spontaneous when compared to the 500 one. Okay, please remember this particular point. Then there comes the next important parameter, which is your delta H, right, which I have used in the Gibbs-Helmholtz equation. Delta H should be negative, right? It should be negative, and more the negative value, more is the spontaneous nature of the reaction. So if delta H is negative, right, and like your delta G, then your reaction is spontaneous. So these two parameters, please remember these two parameters. What I can do, I can write here these two parameters. Your delta G, it must be negative, okay, and delta H should be negative, but it may be positive also, right? But in order to decide the spontaneity of this on the basis of the delta H, sign of the delta H, we have to consider the sign of the delta S as well as the temperature. I'll discuss these things in a little while. Please be in the lecture, right? And after that, you can see my third important parameter. My third important parameter is the delta S, which is the entropy change, and that entropy change should also be positive, and higher the positive value or more the positive value of the entropy change, that is delta S, more is the spontaneous nature of the reaction. Okay, so you should remember these points. These are the very, very important points. I can write here delta S should be positive. Okay, so and sometimes it may also happen that your delta S is negative, right? So this again the reaction can again be your spontaneous reaction regardless the positive and the negative nature of the delta H as well as the delta S. We have to focus on the temperature or the other things. Very quickly we will discuss all the conditions, right, of these positive and the negative signs where we get the different kinds of the reactions. Okay, so these parameters, delta H, Gibbs-Helmholtz equations. And now the Ellingham diagram, you can see here what I have told you already. So guys, this is my metal which is in solid state, and this is my oxygen. I have already told you we are always interested in the smelting process, that is the formation of the your metal oxides or the decomposition of the metal oxide. We are dealing with the oxygen, and oxygen in the gaseous form, they are forming the metal oxide which is solid in that case, right? And please remember, these are the combustion processes, right? Whenever you are actually treating this oxygen with the metal at high temperatures, basically this is the combustion process, and combustion process are always exothermic process, and since these processes are exothermic process, for these reaction delta H is always negative. Here your favorable condition delta H should be negative, so it is negative for these combustion processes. So which this I have written over there. As you can see here, delta H is always negative as these reactions are the exothermic reactions, right? Therefore we need to observe the sign and the magnitude of the entropy change, that is delta S, in order to make delta G negative in the Gibbs-Helmholtz equation. This is the very important thing which you should note down, right? So here you can see I have described some conditions here. I have explained, or I am going to explain some conditions which I have already summarized here. So this is your Ellingham diagram. As I already told you, the Ellingham diagram is the plot of the delta G of formation of the metal oxide, right? This is delta G, okay, and the negative sign is already here, right? So standard free energies for the formation of the oxides. Please remember, this delta G is the standard free energy of formation of the oxides, measured in the kilojoule per mole generally, right? But you may also take this account into, you can also use the different unit like kilocalorie, right? But generally kilojoule per mole is used, right? And this is plotted against the temperature which is in degree centigrade, and these are the different processes when we are getting the metal oxides in that case. Please remember these things, right? This is very important. However, I will come back to this particular diagram again and again as and when required, right? Right now you can focus here. Metal oxides generally have very high melting point than metals, thus they are usually solid. So what is the meaning of that? Say you are having this copper and you are oxidizing this copper with the oxygen, you are getting the copper oxide. So this copper oxide is solid in that case, right? Because it is generally metal oxides have the higher melting point than the corresponding metals, right? Similarly, you can see here, this is your nickel. You are oxidizing this nickel into the nickel oxide, then nickel oxide is also solid in nature. So for any metal, right, whether it is zinc, whether it is manganese, right, whether it is titanium, aluminium, magnesium, calcium, whatever, your metal oxides are always solid, right? So they are solid in that case. So what can happen? Conditions for negative value of the delta G, because we are interested in the standard free energy of the formation of the oxide. So we will only focus on this parameter, and we will try to make this value negative, because this negative value of delta G is the criteria for the spontaneity of the reaction. Say for example, your first condition is like that. Your delta H is negative, which is generally always, because these processes are combustion process, and in the combustion process this delta H is always negative, right? And suppose in the second way your delta T delta S is positive. Now say this T delta S is positive. So what we can do, we can put this negative value and this positive value of T delta S in the Gibbs-Helmholtz equation in order to get the final expression. So delta G equals to negative, right, which is delta H minus, and this parameter T delta S is positive, so I am writing positive here. So this positive, this negative, right, this will make negative here, and this negative and this negative again will give you the negative sign, and this negative sign will have the very high magnitude. We get the very high negative value of delta G, and when this happens, your reaction is the spontaneous process. Please remember, this is positive, this is negative, these two are the favorable conditions, right? And the reaction would be spontaneous in that case, right? And now say suppose in the second case, right, this negative is always, there is no problem in that, right? And suppose now this time your delta S is negative, somehow is the delta S is negative, and in a little while I will show you how we can have this delta S negative value, right? Say this is negative. Again, what we can do, we can put these two negative values in the Gibbs-Helmholtz equations in order to get the final expression, which is negative again, right? So this is negative, that means delta G negative. Again, this is the favorable condition, right? And when this condition is the favorable, that means your reaction would be spontaneous. But here we need to look some of the important parameters. Which parameters? Say in that case, delta H is greater than T delta S. Please remember, in that case, delta H is greater than T delta S. So before proceeding further, what I can do, we can write the we can write the expression here. Delta G equals to delta H minus T delta S, right? This is the general behavior. Okay, right. Here you can see in the second case, this is the negative value. Now suppose this delta H is greater than T delta S. What is the meaning of that? Then we get the negative value of the delta G, because this is the negative, this is negative here, and this is greater than this T delta S. So obviously this negative value will overcome to this T delta S value, and higher the negative value of delta H, higher would be the negative value of the delta G, and your reaction will be spontaneous, right? And in such conditions, your reaction will proceed even at low temperatures, right? So this will obviously happen at the low temperature. See, when this T is low, when T is quite low, right? So this parameter will also be low, very, very low, right? But this value delta H is very, very high. So very, very high. That means very high negative value for this one. So we can, this delta H can easily overcome with this value. So finally, this overall right hand side thing would be negative, which makes the delta G also negative, and the reaction would be spontaneous, right? Now the third condition, I am taking the different kind of the conditions, which is not very much probable, but we can take the example, right? Now say this delta H is not favorable. See, generally we know the delta H should be negative in order to get the spontaneity of the reaction, or in order to get the negative value of the delta G. But here this is not the favorable condition. Say your delta H is positive and your T delta S is also positive, right? This is positive, this is also positive. So what again we can do, we can put these two positive values in the Gibbs-Helmholtz equation. So I have see, we can, what we can do, we can put positive here for delta H, negative sign is there in the expression as I have written here. We can start another bracket, or T delta S is positive. So this overall will give you the negative value, right? This will give you the negative value of delta G, right? And when this will happen, in that case your T delta S should be greater than delta H, right? Because this is not a very, very favorable condition. If your temperature is very, very low, please remember, if temperature is very, very low, that means this parameter will also be low. That means the positive part, right, which makes this delta G negative would be very, very low. And when this would be very low, then this positive sign which is here in that in this third case will overcome to T delta S, and overall this right hand side will become the positively charged, which make the delta G less negative or even zero or positive, which is non-spontaneous. So this at low temperature, this is very bad condition. So this will happen at high temperature. We need to increase the temperature here. So I have written this thing here. In this case, if T delta is very, very high, then delta H, then we get the negative value of delta G, and reaction will be spontaneous, and this will obviously happen at the very high temperature. Please remember this particular point. Now the next thing, so what is written here? See, why the slope of the line representing the combustion of the metals is positive in the Ellingham diagram. Why this happens? So what is the meaning of that? You can see here, this is the oxidation of calcium into calcium oxide. So this is positive slope going up, right? And magnesium, when reacting with the oxygen, again it is going up. Aluminium, when reacting with the oxygen, it is going up. So all the metals, right, all the metals which are oxidizing, right, they have the positive slope. That means they are always going to the uphill, right? I have shown you here actually. So why this happens? Again, this is quite simple. Right now, I have given you the most of the concept used in the Ellingham diagram, most of the concept of the thermodynamics which we generally use in the Ellingham diagram. I have given you all the things. Now it is very easy to decide why the slope is uphill, why the slope is downhill, right? Here what we can see, delta S is the answer. So why the slope of the line representing the combustion of the metal is positive? Your answer is the delta S. That means entropy change. Let us take an example of this very first reaction, right? Here you can see 2 of the calcium reacting with the oxygen and forming 2 of the calcium oxide, right? So here I have written this reaction. You know this calcium is the solid, okay, and this oxygen is the gas, and calcium oxide, as I already told you, metal oxides are always solid. So in that case actually entropy of the system is actually what is happening with the entropy of the system? It is decreasing, right? It is decreasing. Why it is decreasing? You can see here your gaseous reactant is there. You know, see, if you know what is entropy, entropy is the degree of measure of randomness, right? That means higher the random nature of the system, higher would be the entropy. You know, in the solid crystal, your particles are very much aligned or fixed in the particular points. So randomness is quite low. So delta S is low. But if you melt that crystal into the liquid, it becomes liquid. Now liquid will have the little lower order manner, right? Orderly arrangement of the particles. It can float here and there. That means your randomness is increasing. That means delta S is increasing. That means liquid is having higher entropy than the solid. Now again, say if you boil that liquid, right, you convert that liquid into the vapor. That means all are in the gaseous form. They are very fastly and randomly moving here and there. That means delta S is quite high in that case. So here you can see one gaseous reactant is there, right? But here all you can see this is solid is there. That means entropy is decreasing. That means it is going to the downhill side. So what happens in that case? If I take this particular example, most of the metal oxides generally proceed in this way only. This is change in the entropy. This is the summation of the entropies of the products, right? Minus this is summation of the entropies of the reactant. So in that case, you can see here entropy is 0. But here, because it is solid, and this is again, you see the entropy is the 0 for this solid calcium, but for this one it is +1 actually, right? So you can see here this value is basically what? If I put bracket here, so this will give you the negative value, that is -1, right? And this -1, that means this delta S is -1. So we can apply the straight line equation to this. How we can apply the straight line equation of this? This is your Gibbs-Helmholtz equation. Delta H negative I can put here, this negative, and your entropy is negative, so I can put negative here, right? This T is constant. See, this T actually is the variable, right? So we can forget about this T right now. We can only focus on these two signs. So delta H minus will become positive, right? So plus T delta S. Now if you see this particular reaction, this is the equation of the straight line. Y equals to mx plus C, where the C is actually the delta H, which is constant in that case, right? So we have nothing to do with this delta H. It is always favorable. So we can forget about this thing. And T is the temperature, which is the variable, and you can see here we are always changing the temperature. And this is the delta S, which is M. M is what? M is basically your slope. So in that case, your slope is positive. This sign is positive, right? Whenever you do these reactions, right? When you convert your metal into the metal oxides, you get the negative value of delta S, which makes the T delta S positive. So this delta S, which is the your slope, it is positive. That's why these all lines actually, which represents the oxidation of the metals into the metal oxides, are having the higher slope. Okay, I hope this is quite clear now. But again, you can focus here. Some lines are going straight. There is no uphill or no downhill type of thing. So this is the condition of the equilibrium. That means entropy would be zero in that case, right? Please remember, in that case, entropy would be zero. And here you can see this is the downhill condition. Downhill condition, we are observing only for the formation of the carbon dioxide. Carbon reacting with the oxygen, forming carbon dioxide, only this is actually going downhill side. That means slope is negative for this particular one. Why the slope is negative for this oxidation of carbon into the carbon dioxide? Let us check. You see here in that case, this is your carbon, which is solid. This is oxygen. This is gas, and a complete balance reaction will give you the 2 of carbon dioxide, which is gas. Now, if you calculate the entropy change, delta S is the summation of the entropies of the product minus summation of the entropies of the reactant. So here you can see the stoichiometric coefficient with the gas is 2. You can write 2 here, minus 0 plus 1, because this is solid, this is 1, 0 plus 1, that will give you the plus 1 value. Plus 1 value, if you put this plus 1 here, see delta H is here, minus is here, you can write plus 1 here. So plus and minus is the minus. Here in that case, minus sign is there along with this T delta S. That means your slope is negative, right? For this combustion of the carbon into the carbon dioxide. That's why this slope is downhill side like that. So these are the important things which are very, very important, and such type of questions are generally asked in the JEE examination. Please remember, I hope these 2 points are quite clear now. Now the next thing, why we avoid very high temperature in pyrometallurgy? Like this is something contradictory. As I have already told you that your what I told you that pyrometallurgy is the metallurgic process at high temperature, but we cannot increase the temperature too much. Why? Because too much, for the increase of the too much temperature, we need the too much of the carbon or the coal. That means we need the fuel. So cost efficiency would be there and your cost would be very, very high. That's why we cannot increase the temperature that much in the pyrometallurgy too. So what this point I have summarized here, I think. Though pyrometallurgy is a high temperature processes, but we cannot increase the temperature much due to the cost efficiency. However, increasing the temperature gives the more negative value of the delta G. See, if you increase the temperature, right, obviously your entropy will increase, right? That means positive part will increase. This will give you the higher value of the negative delta G. The reaction would be spontaneous. You can verify this by using the Gibbs-Helmholtz equation, right? So, but again, this will however, this is true that high temperature, the delta G would be more negative in order to get the spontaneous reaction, but we cannot increase the temperature much due to the cost of the fuel. Now, another very important thing, phase transition temperature, which is also generally known as the crossover temperatures. However, the crossover temperature is something different, right? So here, where is the phase transition temperature? Let us focus here. Say for example, right, you can see here, if you move along this particular graph, so this is the M. M is what? Melting of the calcium. You can see here this scale is there, melting, element M. So here your metal starts, your calcium metal starts melting, so randomness will increase, right? Randomness will increase just like that. And at this point B, the boiling will start. When the boiling will start, your entropy will rapidly or abruptly change or abruptly increased. Why? Because gas has more high value of the entropy, which is reflecting here in that case, right? That means the slope will actually move sharply in the positive direction. That means uphill to the uphill side. Okay, and again you can see here for this magnesium, this is the melting point, and this is again here B is the boiling point. But if you focus here onto these particular graphs, right? Say first of all, you can see here. So this I have written here, this ZNO, 2ZNO phase transition temperature. So see, this is actually this phase transition is happening here, right? So this I have written over there. So if you want, then you can read this paragraph in order to understand, right, the things. But let us take, say, at point M. See, if you focus on this at point M, for zinc, oxygen, zinc oxide, okay. At point M, melting point of zinc, which is the melting point of the zinc. Zinc start melting and entropy, that is delta S, increases, right? There is no reason, right, why delta S will not increase. And delta G starts decreasing, so your delta G will start decreasing, right? So delta G is decreasing, right? But at the point B, if you come there at point B here, okay, so which is the boiling point of the zinc, we get the vapors of the zinc which abruptly increase the randomness, that is delta S, right? And delta G increases sharply due to this phase transition, and we get the crossover temperature. So this point is which is the point of intersection of the two points. This is cross of this point is actually the crossover temperature, please remember. And here this is again, you see, this is again this temperature is also this temperature. This is also crossover temperature, right? If you extend or if you draw the perpendicular here, actually you will get that crossover temperature. Please remember this point. This crossover temperature is very, very important. Okay, I have explained here. This is the crossover temperature, right? See, this is the plot of your magnesium, and this is the plot of the aluminium, and they are crossing each other here. So this temperature is the crossover temperature, and this temperature is around 1640 degrees centigrade. 1640 degrees centigrade. So let us understand what this actually crossover temperature is explaining. So we generally, with the help of the Ellingham diagram, we use or we select the particular kind of the reducing agent for a metal oxide to get reduced in order to get the pure metal. Basically, we are selecting reducing agent. So how the things works, let us understand. See, first point, the graph of the metal which is placed. See, this is very, very important. This point is very, very important. Students, what you can do, you can note down this particular point in your notebook as trick or the mnemonic, right? If you know this thing, then it is very easy to to predict your better reducing agent. The graph of the metal which is placed lower in the Ellingham diagram can reduce the metal whose graph is placed above in the Ellingham diagram, which is simply means that if you are comparing this magnesium metal and calcium metal for their reducing nature, so this calcium graph, the calcium oxide graph, is placed below the magnesium oxide graph. That means calcium can easily reduce magnesium. Calcium can easily reduce magnesium oxide in order to get the magnesium. So what would be the overall reaction? I can write the two reactions here. Say for example, I am writing the reaction here. 2 of the calcium plus 2 of MgO, and here you are getting 2 of Mg plus 2 of CaO. Say this is your first reaction, and say second reaction I am writing like that. 2 of CaO plus 2 of Mg, and they are producing 2 of MgO plus 2 of Ca. So here in that case, you see this calcium is acting as the reducing agent because it is getting oxidized in the reaction, and the component or the chemical species which undergoes the oxidation basically act as the reducing agent. And in that case, your magnesium, in the second case, this is case 1, this is case 2, in the second case your magnesium is acting as your reducing agent because it is getting oxidized. So which one is the better, which reaction is the spontaneous reaction or the feasible reaction? So this reaction, first one is the spontaneous or the feasible reaction, second one is not. Why? As I already told you, the trick is that, what is the trick? Trick is that the graph which is plotted below in the Ellingham diagram would be the better reducing agent for the metal which is placed just above it, right? So here you can see calcium is the better reducing agent because it is having the more negative value of the delta G. Delta G is somewhere around 1200 for this one, and for this magnesium the delta H is little higher than this one. So more negative value is this one basically, 1201. That's why it is more spontaneous, right? So calcium is better reducing agent than magnesium. Now compare these two. Magnesium is better reducing agent than aluminium, right? But all these things will happen below crossover temperature. Please remember, this happens only below crossover temperature. Now if you compare titanium and aluminium, of course aluminium is better reducing agent because it is placed below. If you compare silicon and your titanium, so titanium is placed below, so titanium is better reducing agent. So in this way you can get the order of the decreasing order of the reducing nature. So calcium is the best reducing agent in this Ellingham diagram, followed by the magnesium, then aluminium, titanium, and your iron is the worst one. This is something very, very important, but please remember, this will happen below crossover temperature, right? See, once we reach at the crossover temperature, then we need to observe graph above crossover temperature in order to predict the reducing agent, right? So this is your crossover temperature, okay? So your aluminium reacting with the oxygen, and so your aluminium reacting with the oxygen forming your aluminium oxide. This is the reaction, okay? And this is the magnesium which is reacting with the oxygen and forming MgO. So these are the two reactions, but crossover temperature is reached. So above crossover temperature, that means above 1640, you can see this aluminium graph is placed lower than the magnesium graph. So in that case, aluminium would be the better reducing agent. So here you can see below 1640 degrees centigrade, magnesium can reduce aluminium, as obvious, because this is below 1640. The normal condition is like that. So this magnesium plot is placed lower in the Ellingham diagram, right? So magnesium can reduce aluminium, but above this 1640, your aluminium is placed below than the magnesium. So aluminium will reduce magnesium now, right? This is something very, very important. But above 1640 degrees centigrade, aluminium can reduce Mg. So these things are very, very important. You need to understand, right? I hope this is quite clear now. Now let us take some of the examples, right? So what are the some of the examples? The correct statement regarding the given Ellingham diagram. This question has been asked in the 2019 JEE mains examination, right? So this is the plot and these are the things. At 1800 degrees centigrade, copper can be used for the extraction of the zinc or zinc oxide. So where is, say this is 800, right? This is the temperature 800 and this is your copper, okay, and this is your zinc. That means you need to consider this one. So this is not possible because zinc is placed below. Zinc is placed below, that means zinc will act as the reducing agent but not the copper. So first statement is not correct. And then the second one, at 1400 degrees centigrade, aluminium can be used for the extraction of the zinc from the zinc oxide. So where is 1400 degrees centigrade? Somewhere here, right? Somewhere here, 1400 degrees centigrade. So if you extend here at 1400 degrees centigrade, so aluminium is actually placed below. Aluminium is placed below and zinc is above. Of course, this can happen. Your second answer seems to be the correct one. Let us check which is the correct one, right? Here you can see from the Ellingham diagram, we can say that any oxide with the lower value of the delta G is more stable. That means more spontaneous than an oxide with a higher value of the delta G. We can also predict that the oxide placed higher in the diagram can be reduced by the element involved in the formation of its oxide placed lower at that temperature in the diagram. It is happening in case of the ZNO for its reduction by aluminium at 1400 degrees centigrade. So your second option is the correct option. In that case, you can mark this second as the correct answer. Okay, now moving to the next one, right? So this Ellingham diagram has been given to you. So this is your question number 6. This is the question from the NCERT. A metals oxide that can be reduced by the Fe as a reducing agent at the temperature T1. So this is the temperature T1, right? And you want to reduce metals oxide, right? So this is as a reducing agent, metal oxide that can be. zirconium which is placed here, and calcium which is placed lower. That means calcium, see at this T1 calcium can reduce magnesium, but there is no question of calcium related calcium and magnesium. Question is like that, metal oxide that can be reduced by Fe. So Fe that can be reduced by Fe. Of course, Fe is placed lower, right? So it can only reduce the zirconium, right? While see magnesium is lower, so Fe cannot reduce this MgO, and calcium is placed lower, so Fe cannot reduce this calcium oxide into the calcium. So this Fe can reduce your zinc oxide to the zirconium oxide to the zirconium, right? So this zirconium is the correct answer. The option number 1 is the correct one. Yes, option 1 zirconium. Now your last question, aluminium can reduce magnesium oxide under the following conditions. Say here above 500 degrees centigrade aluminium can reduce magnesium. So this is where, say somewhere here you are having the 500 degrees centigrade and your aluminium is placed lower, right? See, aluminium is placed above and magnesium is lower. So this is not possible, right? Because this at this temperature magnesium is better reducing agent because it is placed lower. So this option 1 is wrong. Below 500 degrees centigrade aluminium can reduce MgO. At below, see, even below 5 degrees centigrade, right? If you go to this direction, right, below 500, again it is not possible because magnesium is placed lower. So aluminium cannot reduce this. Below 1350 degrees centigrade aluminium can reduce magnesium. Where is 1350? Here you can see this temperature is 1350. And let us check the another example. Above the 1350 degrees centigrade aluminium can reduce magnesium. Above above this, that means here. So if you go just like that, so of course your aluminium is always placed lower, so it can reduce MgO, right? So it can reduce MgO. So let us check. So fourth one is actually the looking correct one, not the third one, right? See, because it is saying the below 1350. So below 1350, again you see magnesium is placed lower. This is not possible. But above 1350, your aluminium is placed lower, so it can reduce magnesium. So fourth option is looking the correct option, right? So this is the answer. Fourth option is the correct option. So this is the complete idea or the complete picture of the Ellingham diagram which you need to understand. I hope you understood the lecture well. Okay, so what you can do, you can make your notes, you can take the snapshots from this particular lecture and prepare for your examination, right? So before signing out, I am requesting you, if you are watching video for the first time, please subscribe the tetrahedron chemistry classes, and if you like the lecture, do share with your friends also, right? And don't forget to like the video. So that's it for today. I'll meet you in the next lecture. Take care. Thank you. Bye bye. Take care.